Hello everyone, I am Hatija and welcome to our presentation. Thank you for clicking on our video today. If you are interested in learning about Lagrange equation from Hamilton principle, you are in the right place. In this video, Joseph and I will be guiding you through the derivation of Lagrange equation. I will cover the first half and Joseph will take over the second part. Have you ever stopped to think about the underlying principle that govern our universe? Imagine a world where the laws of motion were unknown. Then came Hamilton's principle, revolutionizing our understanding of the universe, emerging from the convergence of several influential intellectual streams in the 19th century. Building on Sir Isaac Newton's 17th century foundation of classical mechanics, Joseph Louis Lagrange's 1788 publication, Mechanic Analytic, introduced analytical mechanics. William Rowan Hamilton's research in optics and celestial mechanics led him to seek a unified principle governing motion. He published on a general method in dynamics between 1834 and 1835, introducing a Hamilton's principle. Today, Hamilton principle remains a fundamental to physics, guiding research in particle physics, cosmology, and beyond. From the smallest subatomic particles to the vast expanse of celestial bodies, motion is the fundamental aspect of our reality. But what if I told you there is a single principle that underlies all of these movements, a principle that has far-reaching implication for our understanding of the world and the laws of physics? Today, we are going to explore a Hamilton principle, a groundbreaking concept that has revolutionized our understanding of classical mechanics and beyond. Lagrange equations are a fundamental tool in classical mechanics which allow us to describe a complex system in a unified and elegant way. But where do these equations come from? Hamilton principle provides a powerful answer here. So what is Hamilton principle? I will give you a simple example. If you want to go from Tambaram station to MCC college, you can go from various paths. You can use many paths, but you need an exact path or exact convenient path, right? More simply, I will give you another example. If you are throwing a stone, so the stone is moved in parabola, right? It will move from one lower point and it will come to some certain height, then it will drop down. Just see the graph here. This is the height and time. Y-axis is the height and x-axis is the time. But if you want to identify what is the exact path, for example, there are many paths. Here there are 3 paths and you want to find the exact path that stone can follow. Then you should know the kinetic energy and potential energy for that particular point, which means you are indirectly finding the Lagrange equation. Lagrange equation is nothing but the difference between the potential energy and kinetic energy. So see that small green points here in the curve. If you are finding a potential energy and kinetic energy for each point, and in order to find the whole curve, you are just integrating the points. So what exactly the Hamilton's principle is? In essence, it states that action integral has a stationary value for the actual path and taken by a physical system. So this principle governs the laws of motion with implications stretching from classical mechanics to quantum field theory. As I look deeper into the Hamilton principle, I realize that its significance. It provides a unified framework for understanding complex systems from pendulum to planetary motion. By analyzing the action integral, we can determine the optimal path that a system will take. But how does this relate to Lagrange's equation? These equations describe a complex system in classical mechanics, and Hamilton principle provides us the foundation. As I already said, Lagrange equations are a powerful tool for analyzing the motion, and Hamilton principle shows us why they work. For me, Hamilton principle represent a profound shift in perspectives. So it reveals the intricate web of connection that binds our universe together. By recognizing the unity of motion, we can better understand the world around us. Hamilton principle has far-reaching implication, and also it provides a foundation for quantum mechanics. So where motion is governed by the wave function. So it also informs our understanding of field theory. So finally, we are here to know how the Lagrange equation can be derived directly from the Hamilton's principle. To derive Lagrange equation, we need to parameterize the possible path. So let us label each possible path with the infinitesimal parameter, which is alpha here, where qit comma alpha is equal to qit comma 0 plus alpha eta it, and I is 1, 2, 3 to n. We are labeling this equation as 1. Here, qit comma alpha represent the generalized coordinate, and alpha is the parameter, and eta it is an arbitrary well-behaved function. Eta t1 is equal to eta t2, and we are taking this as a boundary condition. So del qi is equal to eta I t del alpha. We are labeling this equation as 2. This equation shows how the generalized coordinate change with respect to the parameter alpha, as the qi and qi dot are the only functions of t and alpha, which means that generalized coordinate and the time derivative depend only on time and the parameter alpha. So the action integral I is a function of alpha only. So the equation becomes I alpha is equal to integral from t1 to t2 L qi t comma alpha qi dot t comma alpha comma t tt. We are labeling this equation as 3. We expand the Lagrangian L alone by a Taylor series and around alpha is equal to 0. So what is Taylor series? Taylor series is a mathematical representation of a function as an infinite sum of terms that are expressed in terms of values of the function, observatives of the single point. So let f of x be a function that is infinitely differentiate at x is equal to 0. This Taylor series expansion of f of x around x is equal to a becomes f of x is equal to f of a plus f dash a x minus a plus f double dash a x minus a the whole square by 2 factorial plus f triple dash a x minus a whole cube divided by 3 factorial, etc. So in our case, L qi t comma alpha comma qi dot t comma alpha comma t is equal to L qi t comma 0 comma qi dot t comma 0 comma t plus differentiating dou L by dou qi comma L alpha eta I plus dou L by dou qi dot alpha eta I dot dt. We are labeling this equation as 4. Then action integral with Taylor series expression, we are substituting this series into the action integral form. So I alpha becomes integral of L qi t comma 0 comma qi dot t comma 0 comma t plus dou L by dou qi alpha eta I plus dou L by dou qi dot alpha eta I dt. We are labeling this equation as 5 and ignoring the higher order terms, differentiating with respect to alpha.
Integrating the second terms by on the right hand side by parts, that is integral udv is equal to uv minus integral vdu. Then we will get integral t1 to t2 dou L by dou qi eta I dot dt is equal to dou L by dou qi dot eta I dot t1 to t2 minus integral of t1 to t2 n eta I dot into t d by dt dou L by dou qi into dt. This will be the equation sub. Here the integrated term vanishes since eta t1 is equal to eta t2 is equal to 0. This will be the equation 8. Substitute 7 in 6, then we will get dou I by dou alpha is equal to integral of t2 by t1 summation of dou L by dou qi eta I minus integral of t1 to t2 eta it d by dt into dou L by dou qi dot dt. Then it will be into dou I by dou alpha is equal to integral t1 to t2 summation dou L by dou qi minus d by dt dou L by dou qi dot eta I t into dt. Then taking n as common, dou I dou alpha is equal to integral t1 to t2 summation dou L by dou qi minus d by dt dou L by dou qi dot eta I t into dt. This will be the equation 9. Multiply 9 by dou alpha, then it will become dou I by dou alpha into dou alpha is equal to integral t1 to t2 summation of dou L by dou qi minus d by dt dou L by dou qi dot dt into dou alpha eta I into t into dt. This will be the equation number 10. Using equation 2 and remembering the left side is simply dou I is equal to integral t1 to t2 summation of dou L by dou qi minus d by dt into dl by dqi dot dt into dqi t into dt. For I to be stationary, dou I is equal to 0. Since qi's are independent, the necessary condition is d by dt is equal to dou L by dou qi minus dou L by dou qi is equal to 0. I is equal to 1, 2, 3. This is the equation 11, which is the Lagrangian equation. Above is the special case of the more general Euler-Lagrange differential equation, which determines a path y is equal to y of x, such that the line integral I is equal to integral f of y comma y dot x comma dx. This is the equation 12. Y dot is equal to dy by dx. The necessary and sufficient condition. Euler showed that the necessary and sufficient condition for I to have a stationary value is dou f by dou y minus dy dx dou L by dou y dot is equal to 0. Euler derived this from variational considerations. Lagrange applied it to mechanical systems, hence the name Euler-Lagrange differential equation. Lagrange's equation derived from Hamilton's principle. provides profound and versatile framework for analyzing and understanding complex physical system encompassing a broad spectrum of applications in classical mechanics, optics, and control systems. By mastering Lagrange's equation, we gain insights into the underlying principle governing our universe, enabling innovative solutions and advancing our understanding of the world. Let's explore the vast scopes of Lagrange's equation. From physics and mathematics to philosophy and interdisciplinary connection, we will look into the significance and impact of this fundamental concept. Physics and mathematics. Lagrange's equation unite the laws of motion, revealing the harmony between mathematics and physics. In classical mechanics, they describe the motion of particles and rigid bodies. In quantum mechanics, they pave the way for path integrals and Feynman diagrams. The mathematical beauty of Lagrange's equation inspires awe, bridging calculus of variation, differential equation, and geometric algebra. Computational methods. Numerical solutions for Lagrange's equation have revolutionized computational physics. Finite elements, finite differences, and machine learning algorithms unlock complex systems. Simulation and computation advanced research from material science to astrophysics. The synergy between Lagrange's equation and computational methods propels innovation. Philosophical implication. Lagrange's equation raises profound questions. Determinism versus indeterminism, causality, space and time. Do we live in a clockwork universe or a realm of uncertainty? The philosophical insights from Lagrange's equation challenge our understanding of reality, inviting us to ponder the nature of existence. Interdisciplinary connection. Lagrange's equation transcends boundaries, connecting physics to biology, chemistry, computer science, engineering, and economics. Biomechanics, chemical physics, and optimization illustrate the far-reaching impact. Collaboration sparks innovation as Lagrange's equation unifies diverse fields. Biographical and historical. Joseph Louis Lagrange and William Rowan Hamilton, pioneers who shaped our understanding. Their legacy inspires generations, reminding us that fundamental concepts have human stories behind them. Pedagogical approaches. Effective teaching of Lagrange's equation combine analytic mechanics, computational labs, problem-based learning, and visualization. We must inspire tomorrow's leaders to explore innovative and push boundaries. Lagrange's equations are a cornerstone of physics, mathematics, and computation. With far-reaching implications, as we continue to explore and apply this concept, we honor the legacy of Lagrange and Hamilton. This seminar was done by myself, R. Joseph Jesas Chandrakumar, and my batchmate, Atijatul Fatima. We think it will be very helpful for you to go through if you have any doubts on Lagrange's equation obtained from Hamiltonian's principle. Thank you.